This is going to be our introduction to the chemistry of acids and bases. Yes, by the title that you have, you might also be thinking, well, I thought we were doing equilibrium. We are, but we need to get some basic definitions and some understandings in before we go on. Acids are basically sour, and you can see the Latin word there. Bases also have a synonym called an alkali or alkaline, basically bitter. So acids and bases. Let's go ahead and move ourselves along and see what else we can see. We have a lot of everyday uses or applications of acids and bases. You'll see those all listed here. We have three different definitions. Two of which you are going to have to be able to apply. However, this first one is the oldest definition. It is the least versatile definition. In essence, it said an acid donates a hydrogen in water, whereas a base donates a hydroxide in water. It was a limited definition, so we came up with other more comprehensive definitions. The first one is called the Bronsted-Lowry Definition, and we are now going to be defining an acid as something that can donate a proton in water. And literally speaking, we are talking about a hydrogen ion as something that can donate a proton in water. And I'm not going to be able to write on my screen, darn it. Okay, and a base then would accept a proton in water. This is a better theory. It explains how ammonia can be a base in water. So we're going to be able to get to that. Okay, so let's go ahead and see if we can explain this in terms of ammonia. Ammonia is widely known as a base. And so if we're going to try to show ammonia, and why is my pen still not working? Let me see if I can get it to wake up. All right, so ammonia, there's ammonia, NH3. This is what it looks like. And ammonia has two lone pairs right here and right here. Now, the deal with this is a base has to be able to accept a proton in water. And so to be able to accept a proton in water, that simply means that a base has to have a lone pair of electrons. So that would be an H bonding itself to right here, bringing its charge with it. So what it makes instead is NH4 with a 1+ charge. And that's how ammonia is going to get to act like a base and gets included. Previously, the previous definition did not have a way to include ammonia because ammonia did not have an OH. Okay, so our next... All right, so using this theory, you should be able to write weak acid-base dissociation equations. That means that you need to be able to break apart the ions and identify the acid, the base, something called a conjugate acid, and something called a conjugate base. So let's get into what does that actually mean. A conjugate acid-base pair is a pair of compounds that differ solely by the presence of a hydrogen. In other words, the acid is going to lose the proton and the base is going to gain that proton. So we call it an acid conjugate base, acid base pair. Okay, so we're going to practice that a little bit right now. All right, so acids donate a proton. So let's go ahead and take a look at this. Here is our acid, and here is its proton that it's going to donate. And as you know, the base has to be able to accept the proton. So the base is going to accept the proton, and so we need to know what the two acid-base conjugate pairs are. So first, the acid is paired up with its conjugate base because the conjugate base is what the acid becomes after it loses its hydrogen. The base is paired up with its conjugate acid because it's what the base becomes after it gains the hydrogen. Okay, so once again, the conjugate base is what's left over after the acid loses a hydrogen. The conjugate acid is what the base becomes after it gains a hydrogen. Okay, so we're going to move ourselves along. We're going to try it ourselves here. In this example, I'm just looking at what I see, and I notice that NH4 changes into, let me go back because I did not want that to go that far. There we go. I can see, in fact, that the NH4 actually becomes the NH3. That means that the NH4 has donated a proton to the water. So this proton, the H, is actually being given to the water. I can see that happening there because the water becomes the H3O1 plus. So that means this is the acid. It is donating the proton, and this is its conjugate base because it's what's left over after the acid donates a proton. And then here is our water, which is acting as a base this time, becoming the conjugate acid, and that is what the base changes into once it gains one more hydrogen. So we have an acid with its conjugate base, and we have a base with its conjugate acid. And so when we refer to an acid-base conjugate pair, that's what we are referring to. Okay, next. Okay, here's another one, and I'm just looking at what we have, and I can see that it looks like we have the H2PO4 1 minus becoming the HPO4 2 minus. So I can see that those are paired up, and it seems that the relationship has been that the H2PO4 has actually lost a hydrogen or donated a hydrogen. So that must mean that this is the acid, and this is what's left over. So this is the conjugate base, and in this case, this is the water, which is gaining that hydrogen. So it becomes the conjugate acid on the opposing side. Okay, let's try another one. All right, in each of these examples, you notice that we are forming the H3O1 plus. So this species is called the hydronium ion. It lets you know that the solution is acidic, but I want you to know that IB will look at this interchangeably. It can either be written as the hydronium ion, or it can simply be written as H1 plus. As in, if we were to break apart the strong acid HCl into its two ion parts. So HCl, H1 plus and Cl1 minus. And these can be written this way either way. So what we are doing basically is we are not showing the water, even though we know the water's there. Either way you want to write it is fine with us. Me and IB, of course. That's what I mean by us. That's funny. So let's go ahead and try this. All right. Now, what about if we have a base? Okay, so bases, remember, accept the proton. So in this case, I can see that the NH3 is changing into the NH4. That means the NH3 must have accepted the proton. That makes the NH3 the base, and it means this time that our water must have lost the proton. So that means this time that our water is behaving as the acid. So what's left over after the acid donates a proton, that's our conjugate base. And then what remains, or what the base becomes once it collects or receives the proton, that is our conjugate acid. So we have our two pairs yet again. Okay, so let's see about the next one. Try this one. Can you identify the acid and the base and the conjugate acid and the conjugate base? So let's go ahead and try that ourselves. So in this case, I am noticing that the CO3 actually is becoming the HCO3. So that means it must have gained a proton. So that means the CO3 is acting as the base. And that means this is its conjugate acid. And then, of course, the water is donating the hydrogen. So the water is actually having leftovers of OH, and that's the conjugate base. Okay. All right, in each of the basic examples, please notice the formation of the hydroxide. All right, this species is named, of course, the hydroxide ion. It lets you know that this is actually making a basic solution. So that is what you're seeing here, is that while we are not any longer defining a Bronsted-Lowry base as something that has a hydroxide, when that base is in water, it does produce hydroxide ions, as you can see. And once again, you might be going, well, where did those come from? Remember that the base is accepting the hydrogen, so there's our base, conjugate acid, but it is the water that is losing the hydrogen as the acid is donating its proton, so it is the conjugate base, and that's why we can define this. So has this always been the case? Yes, it has. This is not a new, it's just a different way of looking at the same sort of information. Okay, in the following reaction, identify the acid on the left and its conjugate base on the right. Similarly, identify the base on the left and its conjugate acid on the right. So here we go. I'm looking for what has changed. I see the NH3, not what I wanted. I see that the NH3, you guys, the struggle is real. Okay, I see that the NH3 is becoming the NH4, and it has gained a hydrogen, so that must be being the base, and this must be its conjugate acid. I can also see that the HBr has lost the proton, so the thing that loses the proton is the acid, and then what remains is its conjugate base. All right, I am having you practice this a lot because I want you to get used to what this looks like. Okay, so now we can ask it this way. What is the conjugate base of H2S? That means that we are making an assumption that this is being the acid, because remember, the conjugate base is what's left over after it donates a hydrogen. So the conjugate base must be HS1 or minus 1. Is that right? Yes, it is. Because it's what's left over after we take a H plus off. Okay? Now, let's go ahead and write that down. What's left over after H plus is donated? Okay? How about the conjugate acid? All right? The conjugate acid is what is made after the hydrogen plus is accepted. Remember, the base accepts the proton. So in this case, this would have to be our base because it is paired up with a conjugate acid. That means when we add a hydrogen to this, we must be going to have HNO3. That would be our conjugate acid. Okay. All right, so now we have a slightly different way of looking at this, and this is called the Lewis definition. So Lewis acid and Lewis base. And it is a slightly more broad-based way of looking at it, and it is the most recent definition. Acids are defined as accepting an electron pair. Hold on, everybody. Okay, so acids are defined as accepting an electron pair. By that we mean that there is a, I'll make sure I do this right, everybody. I'm just trying to draw water. There's our water, and it has lone pairs right here. So accepting an electron pair would mean that it would be accepting a pair of electrons added to it, while a base would donate an electron pair. So an acid has to have room to be able to accept an electron pair or a pair of electrons, where a base has to have a way of donating an electron pair or have an electron pair to donate. So here we have again the water, and water has this electron pair it can donate. Now that does not mean that the electrons are going to be given away. It simply means that we are going to have a space, an electron pair space, where a proton can be added on there. So that's what that means. This means also that accepting an electron pair for it to be an acid means that, and I'm trying to, okay, so for it to accept an electron pair, it has to be able to, wow, that's harder for me than I thought. Hang on. Okay, so I got myself all tongue-tied, and basically what this is saying is that for it to accept electron pair, it has to have the ability to break apart into a into a particle. In this case, golly, guys, the struggle here is so real. We're going to get back to where we're supposed to be. Okay, here we are. So that means that we end up having to have a hydrogen, which is what we get as the 2 parts of water. And so we would have that hydrogen being able to accept an electron pair because it has room in its octet to be able to accept an electron pair. So that's how the water acts as both an acid and a base. And the terminology for acting as both an acid and a base is called amphoteric. Able to act as both an acid and a base. It has to do with whether or not it's going to gain the H or lose the H. Okay. So here we go. Let's see if we can put that into action. All right. Identify the Lewis acids and bases. We've already said that water can act as both, but we have to be able to identify the rest of these. And so we're going to need Lewis structures for the rest of these. So drawing them out, I've got some NH3 with a lone pair. The presence of the lone pair means it has a lone pair. It can donate to a hydrogen. So this is a Lewis base. Okay. How about NH4? And I'm going to draw it over here. NH4 means that I have 4 hydrogens attached to it, just like this. And we draw it out like this with the plus there. And this one has to be a Lewis acid because it will have a hydrogen that it can donate. In other words, it can donate a particle that has a place to accept a lone pair. So any one of these H's can be the particle that it can donate to accept a lone pair. So H+. All right. HCl has to be termed a Lewis acid because it has the hydrogen to be able to accept a lone pair, so it breaks it apart. NO3 has no hydrogen, but it does have room to accept a hydrogen. So we have, if we were thinking about it like that, no hydrogen means it has to be a Lewis base because then it has room to accept those. And so then we have BF3. And so BF3 is an interesting one because it is set up like this. And that means that it has room in its octet to accept a hydrogen. So this has to also be a Lewis base. But this is the way its normal octet is. And it doesn't have any hydrogen to be able to, it has to be able to accept a hydrogen, but it does not have a hydrogen it can donate. So there's that. Okay. In a gas phase reaction, dimethylamine, let's go ahead and draw it out. We have CH3 and CH3. And that is bonded to an N that has an H here. And like that. That's what it looks like. Reacts with HCl to form CH3,2NH2Cl. There it all is. Okay, so is in this reaction, is it reacting as a acid or a base? And so we have to figure out what we have. I do see this is right there. I do see that. And I do see that my HCl, that has a very real hydrogen that can accept a lone pair of electrons. So I'm going to, by definition, go, okay, that one has to be the acid, the Lewis acid, and that means because it has a lone pair it can donate, that must be the Lewis base. But we need to ask ourselves, can it also be a Bronsted-Lowry acid? For an acid to be a Lewis acid, it has to have an H that it breaks apart into to be able to accept a lone pair. So yes, it can be a Lewis acid, and yes, that can be a Lewis base, but can it also be a Bronsted-Lowry acid or a Bronsted-Lowry base? So we've already said this has to be a Lewis base, so we can cross out the acid part of things. But now, can it also be a Bronsted-Lowry base? In other words, can it accept the hydrogen? And yes, it can accept the hydrogen, and it does actually accept the hydrogen in this case. So we end up with that D is our correct answer. It is being both a Lewis base and a Bronsted-Lowry base. Okay. So in the next one, on your final question for this Ed puzzle, identify from this list of molecules and ions which two behave as Lewis bases. And so there are your answer choices, and we will have you answer in terms of that one on your Ed puzzle. The final question here, the chemical reactions below show the reaction of AlOH3 as a Lewis acid and as a Lewis base, and the answer to how would we define this, and we've said already that would be amphoteric. Please go ahead and give that one a try for number 2 there. Okay, one final part that I feel that is needed to be discussed is whether or not an acid or a base is considered strong. And I need to, let's see here. Okay, so we're going to start, and this is going to be the part of the notes I'd like to go over right now. So what we need to be able to answer is what does the strength of the acid mean? And you might be interested to know that it is not talking about how corrosive it is. Instead, it is determined by the position of the dissociation equilibrium. So, for instance, a strong acid would have this is going to be one of our strong acids, and it would have 100% of its ions break apart. So, and you'll notice I drew the arrow as in a single direction arrow, as in there will be no equilibrium. It will be so strongly acidic or a strong acid that all it's going to make is the H1 plus and the Cl1 minus. And that graph is like this one right here. That is going to be very large K value and very dissociating completely in water. What about a weak acid? So a weak acid would be something like HF is one of our weak acids. And weak acids we would draw using a forwards and backwards arrow because only a very small amount of it is going to break apart. And so its K value on this case is going to be very low. Value, there we go, will be very low. In other words, it's going to favor the reactants instead of like a strong acid strongly favoring the products. Okay, so let's take a look at the rest of these notes because we're almost done here. I just want to make sure that you know the definition of strong and weak acids. So let's go ahead. I really want this to move, and it's not moving readily for me. Okay. So we've talked about weak acids and weak bases already. The list of strong acids are going to be here for you to make sure that you know them. Strong acids are included in this list: HCl, HI, HNO3, H2SO4, and HClO4. There is one missing. We should also include HBr in the list of strong acids. Okay? Everything else is considered a weak acid. Okay? Something to know, strong acids make weak conjugate bases. So strong acids make weak conjugate bases. You should definitely go ahead and make yourself the list in your notes for the strong acids. Let's go ahead and move ourselves along here. Hold on, having trouble with myself here. There we go. Okay, strong bases. Strong bases are going to be pretty much all the hydroxides of group 1A and 2A metals. So otherwise, it is just going to, if it's not a hydroxide of group 1A or 2A metals, then it's all weak. So the stronger the acid, the weaker its conjugate base. That also means the stronger the base, the weaker its conjugate acid. And here is just a really good chart for you to describe and compare. A strong acid has a large Ka, where a weak acid has a small Ka. Strong acids are favoring far to the right. Weak acids favor far to the left. And we'll get into this kind of stuff much more, but I just wanted you to know the difference between strong and weak acids. And we will not be going on here. This is the end. Thank you very much.